Hello, everyone. As Andrew said, I'm Elena Glassman. I am a postdoctoral fellow at the UC Berkeley Institute of Design, and I will be starting my Moore Sloan Data Science Fellowship shortly when I get back. I like to think of myself as a data scientist for code, but I'm also trying to expand into other types of technical solutions. So today I'm going to tell you about, since I'm coming from a human-computer interaction background, human-centered clustering and visualization of student solutions for personalized feedback at scale. But if I could rewrite this title today, maybe I would call it just Teaching and Grading Massive Technical Classes, because I'm going to show you some recent work expanding beyond code that come from massive classes where we're selecting data-driven sets of diverse examples with which to both learn about our students and to help our students learn. Okay, so probably don't have to tell many folks here that our introductory programming classes can be quite massive. I don't have the numbers here for online classes, but even in residential, large research universities, we're pushing into the thousands. And to give you an idea of the scale and type of data that are being produced by students, namely, or when I say data, I'm specifically talking about solutions right now. This is an example of a short function that students will write at least a couple times a week. It might exponentiate a number. It might compute a derivative, where this is this input poly is a list of list of numbers that represent a polynomial, or it might compute a logarithm. So this is these small functions written by hundreds or thousands of students are the data that we're going to really be thinking about for the most part today. So it's hard to make sense of this massive population of student code submissions, because either we can kind of do the traditional thing, which is get a server dump of all the submissions students have generated, where you can look at them one by one, but it's hard to get the big picture. Or you can attempt to get a big picture. This is one, I think, early but common approach, which is to represent each code submission as a point, right? We've reduced a lot of text that represents a given solution into a single point in this space, which is hard to describe, and then connected each node, whether if it has a certain small number of triadic distances between one and another. So it's still not really clear, if I were a teacher, how I would go from something like this to, okay, well, the people on this side of this lobe, they got this particular thing wrong. I guess I have to help them with a certain message, right? So it's not entirely clear how you make use of this kind of visualization. So tailored feedback in a massive classroom is hard because the teacher is providing assignments and feedback, and the students are producing too much data, in this case code, to read. So the way I've been approaching this is to represent solution commonalities and variation from the data produced by students for the teacher to better understand what their students are doing, and help the teacher then create more tailored feedback and perhaps even new assignments for the students. So that represents the systems piece of this. But I also want to talk about, since we're in advancing education with data, right, like the education part. Right? I'm a computer scientist, but I want to tell you a bit about what I've learned from reading up on the learning sciences and literature that has helped inform the designs of these systems. Right? So if our goal is to promote human learning, then we have to care about the humans. And so I'm going to make use of literature on how people reason about examples that are drawn from populations to make inferences about the underlying population. So we can be careful about how we synthesize these examples of student code, and we can render them in contrast with each other to help the teacher actually confidently grasp. If you think about like interpretable machine learning, be confident that they understand the thousands of students' solutions, so they can learn about their class. And likewise, perhaps help the teacher produce class-wide postmortems or personalized code feedback using explicit examples from the class, sending those back to individuals in a tailored way such that the students are also able to, from those examples, best learn what the teacher's trying to communicate about code. So The system challenge here is to support human learning from examples in the way that we design the system itself. I'm going to talk primarily about two systems that I did during my PhD thesis called Overcode and FUBAS. They're kind of two skins on the same underlying machinery, and then I'll talk about our attempt to generalize this to LaTeX, where you can't execute code. Okay. I also want to talk for more than is typical for a technical talk about how humans learn from examples, so that we can then talk more principally about how we mine sets of examples that are both maximally helpful for those students and derived from that massive quantity of student data that we already have. Okay, so also for folks in the room who have looked into how to help students teach, I mean, there's a lot of work on intelligent tutoring systems and self-explanation, pretest priming, one-on-one tutoring, right? There's a lot of literature out there to help people. And so I am not going to try to help folks with anything but this one last principle here, which I think is very powerful, which is how we represent ideas, concepts, such as what is good code versus bad code, using specific examples that vary in superficial ways, perhaps, but are consistent in that which we're trying to communicate. So the whole proposition, of variation as a teaching tool is that by having students or the learner engage with a set of diverse examples, you can help students form better mental representations in their own mind, which will generalize to new problems and facilitate transfer to new situations, right? So they don't get thrown off by superficial differences about a new problem that you give them. The learning benefits of example variation have been found in many academic domains, so we're not going to verify that with our systems. The learning scientists are already pretty confident that this is a robust way to help. You see it in mathematical equation solving, in geometric reasoning. You even see it in non-more humanities style work, where folks are learning negotiation by studying case law. Or like specific negotiation case studies. So they're even looking at, essentially compare and contrast exercises help students generalize and become more robust in their learning. Okay, so yeah, a lot of different areas. So we already, for code learning, create manually sets of examples that try to define something that's a little bit hard to explicitly spell out, like what is Pythonic style, right? Here, this Pythonic style of be explicit. They give a good and a bad example, so that's a fairly straightforward way of using variation to help the student understand what be explicit means. In one case, I guess they're using all sorts of fancy syntactic tricks, whereas the second case, they're spelling it out quite literally as to what's going to happen to the inputs and how they're going to return. And here's another example of the good and bad. This is just the simple variation method, where you show things that are inside and outside of the concept you're trying to communicate. And then there's kind of more nuanced ways to make use of variation. So here, this is 5 different ways. In here, there are 5 different ways to use the unpacking feature in Python. So this is not saying, this good, that bad. It's saying, hey, here's the design space that you have to work in. And these are carefully curated and constructed so that the student can see what about the syntax makes one different from the next, or not. Okay. So in order to use diverse sets of examples in an effective way, it'd be helpful if we understood exactly what about variation was so helpful, right? If we understood the underlying mechanism, where we have a notion of the dissimilarity metric we need to be maximizing here. If we want to maximize variation in our examples to facilitate robust learning, then we need to know what's the metric, and also how different do we have to be on that metric to be effective. So for this, I'm going to try to wake you up a little bit with a reference to Arrival. Who's seen Arrival? Okay, if you haven't seen it, I highly recommend it. It's The premise of the movie here, and I hope you'll see the analogy here quickly, is that a professor of linguistics has been called by the US government, aliens have arrived, hence the name, okay, and they don't speak a word of English, right? So she has to, given her knowledge about languages, enter and start, essentially she'll write human, and then the other human will be like, this is me, like trying to communicate, what does it mean, abstract, through example, that I'm a human, this is not, right? I think she's kind of making use of the same techniques potentially. So essentially, I'm gonna now teach you as much as I know about strategic diversity of examples through examples. Okay. So we're going to learn the educational value, the definitions of some language that I found from learning sciences to be very helpful, specifically this notion of structural and superficial features of examples, and finally strategies for composing diverse sets of examples, whether you're doing it by hand or if you're building systems to choose those diverse sets. Okay, so if you have a single example, like I'm going to teach the alien, since we've got a bunch of laptops here, we can say, all right, the aliens have arrived, we'll teach them about what a laptop is. I show them this laptop, it's got certain shapes and colors and sizes that this learner can parse. And then we can ask it, hey, is this also a laptop, right? And the problem with generalizing from one example, as you might know from like general machine learning or teaching, is that it's not really clear, right, what defines a laptop, what is incidental. So, by the way, I'm just going to mention that this is analogical transfer, right? Going from something you know to something you don't know. This new object is similar in certain ways. It has shared features and distinct features. If we were in a human, one of the reasons why humans prompts are so good is we have Bayesian priors on what is and isn't important here. But if the student is really new to something, right, they don't have any sense of that. And so once we say, yes, this is also a laptop, they can start generalizing more robustly from these two examples and say, okay, maybe these shared features are what we're going to say critical, and the distinct features are irrelevant. Right? So it's kind of the hypothesis to move forward from there. So the learner can detect aspects like color, shapes, and sizes, and starts finding points along those dimensions of variation that the human will, or the learner will start to believe are matter or don't. And finally, if you're generalizing from those two examples using feature sets like shape and size and whether or not it has a hinge, do you guys think these are, who thinks the top one's a laptop? No? Okay. We're getting some shaking of heads for the top, and the second one?
I guess if you have a really big lab.
Okay. Well, I have a little bit of fun with this. So, our critical features from these first two laptops were that they had a grid of rectangles, which is a keyboard, and they had a hinge. Well, the top one has a grid of circles, and the second one, it looks like a laptop, but in fact, the top one is a working Raspberry Pi powered steampunk laptop, and the second one is a facsimile. Okay, but the reason why we failed here is because our first two examples did not fully capture the structural features of what a laptop is, right? The structural feature is actually that does computation, okay, and the superficial features are mostly, don't matter, right? So you might need to show, there's ways in which we can omit information initially that can create misconceptions. And so being strategic about how we construct these sets is really important. Finally, so if we have a strategy for inducing a good mental representation of the learner's mind, we can, borrowing from variation theory by Martin et al., which is a nice summary of these ideas, we can first show examples that do and do not belong to the concept we're trying to communicate. This is the, be explicit, this good, that bad. We can show examples that vary superficially. In this case, these are all working laptops, okay? But there are things that they don't share that maybe the learner can learn or can hypothesize are irrelevant. We can help them separate dimensions of variation by showing for each dimension, in this case it's color. Like show everything else being constant while varying along the full width of that particular dimension of variation. And finally, what they call fusion, just vary everything, right? Because that's more like the real world. So these are ways that you can strategically vary your examples to help induce a good mental representation of the student's mind. Okay, so the students that get sets of strategically diverse examples will hopefully infer the better mental representation, promotes comprehension, abstraction, generalization, transfer, all the things that we want from people if we're using a system to help teach them. Okay. Also, I just want to note that being an expert or a human, since I'm a human-computer interaction person, I want to point out the fact that coming up with a good set of a strategically good set of examples requires some amount of expertise, right? Being a novice, this would be hard to crowdsource, for example, right? So there's a role for the expert in these systems. Okay, so how can we mine these sets of examples from data we already have? We have students that are submitting hundreds of code that either has or does not have the ideas about programming that we want to teach. Maybe we can make use of what we already have. So let's first talk about overcode. This is, so back in fall of 2012 when edX was just getting off the ground, 3,842 people correctly implemented a function that iteratively computed base to the exponent. Or rather, I should say, was supposed to iteratively compute base to the exponent. But 1,538 did an iterative solution, 26 did a recursive solution. And one, well, there was a lot of special snowflakes there, but we're a little bit lost. But they did, all of these are marked as correct by the autograder. Okay, so if you want to go beyond what the autograder can teach them, which is this, you need to do some more analysis. So randomly selecting code examples will not necessarily help the teacher learn a complete picture of these student solutions, because the probability that the teacher sees that a subset of their students are also finding iterative or really also even more cool ways to solve it is very low. And it's also not going to produce diverse sets of code examples for the students. So if you were just randomly picking, everyone would just see the iterative example probably. All the cool variations for how to solve this problem would get lost. So one way to help us find the cool variations, to find like a diverse set of examples to capture how your students, how students came up with solving this particular problem. We can take these dimensions of solution variation, like the formatting, their comments, the variable name, statement order, and syntax, and let's collapse some of these dimensions to leave one dimension that we can talk about with students at kind of high level. So we can standardize formatting, remove comments, do a human-friendly canonicalization of variable names, which I can explain later. We can ignore statement order when it doesn't affect the behavior of the execution, for the most part. And that can leave syntax. So we say syntax might be able to capture a great deal of the variation in how people approach solving this problem. By the way, this is documented in great detail in our Tokai 15 paper. Then you can get something like this. So, so this is the, I shouldn't have hit refresh, it's a little bit slow. This is the overcode interface, and it is tweaking hard to render, there we go. So here's the 1,538 solutions. I'll make this a little bit larger. If you've read this single kind of canonicalized solution, then you've read 1,500 of these, okay, where you didn't have to worry about the fact that there are Polish students using the word wynik instead of result because they're Polish. But you can essentially say you read all of those just by reading the single, this cluster is represented in a human readable way by this one representative. And then we have remaining stacks, which are smaller, and we're highlighting the differences. In this case, results, this is a slight difference in terms of whether you're using syntactic sugar. If you taught a lesson about syntactic sugar, maybe you would want to show that. If you hadn't, maybe you'd want to ignore that. Let's see if rewriting works today. But yeah, so essentially the teacher can choose the syntactic aspects that they care about, and through rewrite rules, find the aspects that they don't care about and erase dimensions of variation in syntax that they're not going to be thinking about at that time. Oh, okay, so that worked. My goodness, sorry. Demo effect always hit a little scary. So now, once having ignored the fact, we said we don't care about syntactic sugar today, you can see that you've got 1,900 students who are essentially just solving it this way. We can sample that once and then explore the interesting variation that is less common that may capture, the fact that, well, a huge number of your students are using while, very few are using for. Maybe that's a function of how you taught while or for. Maybe that means you haven't taught for very well at all. Some small section of students are copying a value that's being passed into the function before they're using it, which is good programming practice. Here's those 26 now. They pop out, right? The recursive solution that's interesting that you might want to use as an example in class is easily found. So, so this is one system where I try to collapse the variation that's not interesting to highlight the variation that is interesting and could be used to talk about approaches to solving problems. Okay, so we asked whether or not overcode could help teachers learn a more full picture of student solutions, and also whether overcode could help students find diverse code examples to comment on and present back to students as kind of a post-mortem, a design studio about syntax. And so we brought in 12 programming teachers who unfortunately reflected the male bias that we have at MIT. Many of them, a small fraction of them were about to become TAs rather than had already TA'd, but they had sufficient programming experience to give feedback. We used the inner power example that I've been using as a running example, but also a string manipulation program that was part of a Hangman homework problem, and also the compute deriv function that I described earlier that was the most difficult, where you take a string of numbers representing coefficients of a polynomial and compute the derivative. And these all had over 1,000 solutions. With this particular pipeline, they could be processed on a machine of equivalent power to this MacBook in 15 minutes or less. So that is a big difference from earlier approaches, by the way. When I first mentioned the tree differencing algorithm, that required a cluster overnight because pairwise computations of tree at a distances is expensive. We do not require that. So we used a control interface where we just nicely rendered the individual solutions without trying to collapse any dimensions of variation, and had people scroll through or use Control F in the browser to navigate just the raw, what you would typically have. So we asked them to identify the 5 most frequent but distinct strategies used by students to solve the problem. And for each strategy, we asked them to write, to capture a small code example, write a comment about what the student was doing well or poorly, and also to rate their confidence as to whether or not that truly was a frequent, like something just, a non-trivial kind of, not a one-off kind of pattern. This is an example of a graph that we received from that study, where you can see, at least for the simple inner power solution, people in the control condition feel much more comfortable to skim very quickly. This represents how many, they're essentially scrolling very quickly through the Chrome, the control, whereas they're going very slowly through a much higher variability set of solutions in overcode. Because overcode's got this deduped aspect to it, and it's sorted by popularity, whereas the control is kind of randomly ordered, and they're seeing a lot of the same, but slightly different. And same is true for Hangman, but as soon as you get to something like the compute deriv function, where reading the solutions, you can't just kind of glance at them and say, yeah, I think I know what they did. It becomes much more quick for you to look at these synthesized solutions so that you can, since they're rendered in contrast with each other, they have these canonicalized variable names. You can actually see many more solutions rather than looking at them randomly. So this seemed to have a benefit once you got beyond the kind of fairly trivial introductory exercises. And then if you give people credit for having read the whole cluster by reading the top solution that represents the entire cluster, then you can see that people can read the equivalent of 64% of the 3,800 solutions when they were looking at the overcode condition. 25% of the Hangman was a little bit more complicated, and 14% of the comp deriv functions, right? 14% of something like 1,400 solutions that they've effectively read by looking at the synthesized solutions where those dimensions of variation we didn't care about so much were collapsed. This is okay. I'm gonna go a little more quickly because I'm running out of time. And so we also to ask the question as to whether or not teachers felt like they were learning about the underlying population of students by looking at the solutions they could see in each of these interfaces. They much more strongly agreed with this statement that the interface helped them develop a high-level view of students' understanding misconceptions when looking at the overcode interface as opposed to the control. The answers to our questions were yes. And we're this fall deploying a customized version of overcode for UC Berkeley's 1,500 students this fall. So FUBAS is an example of, so that was about how we could help teachers learn from the vast number of students, right? And now let's see if we can help teachers compose diverse sets of examples to help teach their students the other way. Okay, so that's FUBAS, which was published at the User Interface Software and Technology Conference in 2015. The teacher was really good at bad examples to clarify what a good variable means for a given role in the program. They curated these sets of diverse examples, and then this is facilitated, of course, by the system. When the student submits a solution, they receive a relevant, curated set of examples of variable names for a variable that fulfills a particular role in their program, right? Whether that's a counter or some sort of accumulator, that kind of thing. So this is essentially uncanonicalizing the variable names in this set of dimensions that we represented the solutions, and collapsing the syntax that we say we're not going to pay attention to in this view. So just in case, to just emphasize the nuances here, names cannot be judged on their own. Their role in the computation matters. I is idiomatic for something that's going over the integers that represent the the positions in an array, but it's not a good set for it's not a good name for the values in that array. And so little things like this can really trip up students. So we need to give them feedback on variable names conditioned on the role that each variable plays in the program. And they cannot always even be judged on their own because their context matters. The variable names that they co-occur with matter. So in the teacher-facing interface, people could see each variable role in the program with all its alternative names that happened in all the students' code. And they could annotate them as individual examples to curate their set of diverse examples to send back to students. Curation like this, and then the student would have one of their, when they submit, the student has one of their names wiped away and say, hey, like, what do you think of these names to plug into this placeholder we put here. They can, by hitting submit, they're not getting necessarily a grade, but it's just comparing their judgment of the value of this variable in that role to the teacher's composition. And the teacher may have not given feedback on their specific original choice, but their choice can be mixed into these, so that they can kind of, especially if there's been a little bit of a break between submitting and getting this quiz back, they can actually kind of take a step back from their own choice. I'm going to skip over the user study for this. Okay, I'm going to really quickly tell you about our attempt to work on student solutions, which are derivations to mathematical derivations for machine learning classes, right? So now you can't execute student solutions. You can't automatically tell that they're correct, or look at the behavior of variables to infer what role it's playing in the program. And then you can see I've tried to use color to annotate the analogous points in 2 different student derivations. This is joint work, by the way, with Cindy Tan, Juan Quiras, and Fernando Yoshi-Velez, that there's some variation here that matters, and there's some variation here that doesn't. So we have a couple hundred LaTeX submissions from Harvard's machine learning course. It's not executable, but it's at least parsable, so you can create, just like you have an AST, you can have a math syntax tree. And there's a lot of variation in how people represent the same idea. Some of it is variation we care about, some of it isn't. Human graders, again, because I'm a human computer scientist, they're really critical. They can help teach the machine which variation is going to matter. And this formulation, which I cannot possibly explain to you in the time that I have, will be uploaded to the site as soon as we fix a few details. We hope to make progress on that soon. The final thought is that I hope that the value and role of strategically diverse sets of examples are something that I was able to communicate to you, and I hope through analogical transfer you can see the potential value and role of strategically diverse sets of examples, whether they're automatically mined or selected with the help of the system in your own research. So thank you very much.